All right, here we go. AP Physics video 6.2. So we're getting back into circular motion here. So the first chunk of this is going to really be a review of stuff we've learned in honors and even some of it that we've learned earlier this year. But there's definitely some new stuff here. So kind of tough it out through the review stuff because you got to get to the end of the video, okay? So some review stuff. So last year we learned that if you've got an object in uniform circular motion, then you can find the velocity or the speed of an object in circular motion by taking the circumference of the circle and dividing it by the time it takes to complete one circle. Or you can take the circumference of the circle and multiply it by the frequency, right? Like how many times it completes that distance per unit time. All right, and so last year we did a whole bunch of examples with fuzzy B. So imagine we've got, so here's me. Whoops, that'll work. Here's my arm. And then we're spinning the B around. Here's the B, so it's going around in a circle like this, right? And here's me, I'm happy. All right, so let's suppose that he's got a radius of, 0.75 meters, and maybe he completes, let's say, 8 revolutions in 10 seconds. All right, so if we want to find the period, remember the period is the time for 1 revolution. So if 10 seconds is the time for 8 revolutions, 10 seconds for 8 revolutions, that's the same as 1.25 seconds per revolution. So we just say the period is 1.25 seconds. All right, then to find your frequency, it's just the reciprocal of that, right? So we want to figure out your frequency. Oh, sorry, I didn't write this. Remember, period is capital letter T, if you don't remember that. So your frequency is the number of revolutions per second. So in this case, we're completing 8 revolutions in 10 seconds, so divide it out and you get 0.8 revolutions per second. And we always just call that hertz. Okay. So now what we can do is find the velocity, right? You can use the velocity by using either of these two equations. So let's use the 2 pi r over t. Set v equals 2 pi r over t. So 2 times pi. The radius of the B's circle was 0.75 meters. It takes them 1.25 seconds to complete that path. So divide it out and you end up getting 3.77 meters per second. Okay? All right, and then there's this other blank here for acceleration. Well, I just finished saying that it was a uniform circular motion, which means the speed is constant. Remember, that does not mean that the velocity is constant. Okay? So we need to talk about what's called centripetal acceleration. So remember, that's the acceleration the object experiences due to the change in direction required to go in a circle. All right, so it turns out that to calculate centripetal acceleration, it's just v squared divided by r. Deriving that equation does require a bunch of geometry and a little bit of calculus. I'm happy to go over it with you if you want. I don't know that it's really that necessary, though. So for us, we can find the B's acceleration by taking his velocity, which was 3.77 meters a second. Don't forget to square it, and then divide it by the radius of the circular path. Okay, and so if you do this, you end up getting 18.95 meters per second squared. All right. So at this point, we've talked about sort of describing describing the circular motion, but we haven't talked at all about why the object travels in a circle, okay? So, as a reminder, oh, I'm having a tough time today. Any object that's moving in a circle is always changing direction, right? And so that's what results in our change in velocity. That does mean that the object is accelerating, okay? And since the object is accelerating, that means there must be a force causing the object to accelerate, right? There has to be a force causing the direction to change, all right? And so in circular motion, we call that force centripetal force. So the centripetal force is the name of the force that causes an object to change direction while it's going in a circle, all right? And so to calculate it, it's exactly what you'd think. It's mass times acceleration. And if we remember that acceleration is v squared over r, then you can find centripetal force by doing mass times centripetal acceleration. Okay. All right, so continuing that Buzzy the Bee example, if we want to find his centripetal force, we would have to take his mass and multiply it by the acceleration. So his mass is 0.25 kilograms. his acceleration was 18.95 meters per second squared. So multiply that out, and you will discover that the centripetal force is not written anywhere on my piece of paper here. I don't know. What do we got? 18.95. All right, so you get 4.7 newtons. Okay. All right, so great. So that's how the calculations work, right? But this doesn't really tell us anything, right? So the big thing we talked about last year was, in addition to doing these calculations, we also talked at great length about, like, what is the centripetal force? Where does it come from, right? And so we looked at this drawing a whole bunch last year. So this, you know, represents Buzzy the bee traveling around in a circle, right? And the idea is, if there was no force on him, then he would just follow a straight line path, right? So like in this instant right here, the bee is traveling that way. If there was no force on him, he would keep going that way. But he doesn't. So there must be a force acting on him. And that force pulls him inwards back onto the circle, right? So now he's going this way. He wants to keep going that way. He doesn't keep going that way, so there must be a force pulling him inwards. Okay? So it is super important that you identify where that force comes from. You have to be able to describe the centripetal force, right? So we did a bunch of this last year. We did a whole bunch of this. So some examples we talked about were the hammer throw, right? We had the athlete pulls the hammer inward, right? Just like the, you know, pulling the bee inwards. On the rotor, if you remember, it was a ride where you're like, it's this giant tin can, top view, you're looking down at this thing. So here's the top of your head. So at this instant, you're going this way. You can't keep going that way because the normal force from the wall pushes you inward. Okay, so on the rotor, we would say that the centripetal force was equal to the normal force from the wall. All right, I guess here, for the hammer, we would say the centripetal force is the tension in the chain. The salad spinner was exactly the same, right, as the rotor. The centripetal force is the normal force from the wall's little salad spinner thing. If you've got a kid sitting on a merry-go-round, then, so here's our drawing, here's the disc, here's our kid sitting on the merry-go-round. All right, so if they're not hanging on, there's something preventing them from sliding off. And so what's preventing them from sliding off is the friction. So in my case, the centripetal force is your force of static friction, right? Same thing for a coin on a record. Moon orbiting the Earth, you know, what prevents the moon from floating away? Gravity, right? So in that case, your centripetal force comes from gravity. A car on a flat circular track, again, you've got friction preventing your car from sliding off, so your centripetal force would be your force of static friction. Oops. All right? But in all of these examples, and this is what's going to be different this year, in all of the examples we did last year, you could attribute the centripetal force to one specific thing, right? In each of these examples, there's one object applying the centripetal force. But it turns out that's not always true. All right, here's another example. Imagine you've got a car on a banked circular turn. Okay, so here's front view. So here's the headlights of the car. Here's the wheels. Here's the driver. Hello. Okay, so he's driving out of the board at you, right? Driving around in a circle this way. Okay, so what's happening is gravity is pulling him down, right? If he goes too quickly, he's going to slide up the ramp, and so there must be hopefully static friction preventing him from sliding up the hill, and there's also a normal force, right? So in this case, look what's happening. This normal force has a vertical component and a horizontal component, and my friction has a vertical component and a horizontal component. And it turns out, if you remember, your centripetal force always acts inwards towards the center of the circle. So in this example, the centripetal force is actually the combined effects of the horizontal component of the normal force plus the horizontal component of the static friction. All right, so we would say here, the centripetal force is the force of static friction, x, plus the normal force in that x direction. Okay? So this example actually turns out to be very, very complicated because your static friction is variable. So we won't actually be doing examples like this numerically, but we will certainly be seeing other examples where your centripetal force is not caused by just one force, but by the combined effects of two forces. All right? So let's do an example with numbers. All right? Oh, shoot. I guess I should say one other real quick thing here before we get to that example. I guess just remember, so like when you think about the salad spinner example, right? So here's your salad spinner. Okay, it's spinning around like this, right? So if you've got a piece of lettuce, I will draw green to represent the lettuce. The idea is the lettuce wants to go in a straight line. It doesn't fit through the holes, so the walls push it inwards, right? So why does the water go up holes? Well, here's a water molecule. So at this instant, the water molecule is going this way, but the difference between the water and the lettuce is that the water can fit through the hole, right? And so what happens is, the reason the water goes out the hole is not because there's something pushing it out. The water goes out the hole because it's nothing pushing it in. Because there's no normal force. Whoa, what did I just write there? There's no normal force pushing inward. Right? Because when it comes into contact with a hole, that's the same as removing that normal force. All right? So please remember that when you have a thing traveling in a circular path, there's nothing pushing it outward. All right? The whole reason that it would be traveling in a circle is because something's pushing it inward. And if you remove that inward force, that's when the object goes flying. All right, so let's get back to that idea of having two forces responsible for your centripetal force. All right, so there's an episode of The Simpsons, and I'll attach a link to this video on my website. There's an episode of The Simpsons where Homer and Krusty the Clown go around a loop on this tiny little bicycle. Okay, and so they're traveling in a circular path. All right, so suppose we've got this. Suppose I tell you that the radius of the loop is 1.2 meters. And for simplicity, although this is probably not accurate, let's assume that their velocity is fixed at 4 meters per second. Okay? So, and I guess further to simplify it a little bit more, let's not worry about the fact that there's sort of a start and an end to the track. Let's just draw the circle that they're going to follow a path in. Okay? So what we want to do is we want to make a free body diagram for Homer and Krusty, both at the top of the loop and at the bottom of the loop. All right? So at the top of the loop, they're going to be here, right? And so let's think about what forces are acting on. Well, gravity is pulling them down with a force of negative 9.8 m, right? I'm going to actually use the number 9.8 here. Okay? And there's also, the track is above them, right? Look, the surface of the track is up here. And if they're still in contact with the track, then it has to be pushing them. And in this case, it actually pushes them down. Because that's an inanimate surface, we call it normal force. All right? So in this example, both gravity and normal force are pushing down on Homer and Krusty, right? So, super big idea. I'm going to write it in blue. So, in uniform circular motion, the idea is we're not speeding up at all or slowing down at all, right? Our velocity is always 4 meters a second. So anytime you're in uniform circular motion, all acceleration, all of the object's acceleration is centripetal acceleration. Centripetal acceleration, all right? And so the reason that's important then is if it's true that our centripetal acceleration is responsible for all of our acceleration, that means if I multiply those both by mass, I get the same thing. And therefore, it must be true that my centripetal force is equal to my net force. Okay? So all year we've been doing this net force equals net force thing. We're going to do the same thing now. Okay? But the big change here is because we're in uniform circular motion, our net force is actually our centripetal force. Okay? So let's take a minute and let's go up here and find our centripetal force. So centripetal force is mv squared over r. So our mass, we don't know, so we'll just leave it as m. our velocity is 4. Oh, if we square it, divide it by a radius of 1.2. If you do this, you find out that your centripetal force is 13.3 m. Okay? So, why do we care? Well, let's get rid of this. Buy ourselves a little space on the board. All right, so what that means then is when they're at the top of the path up here, as I've illustrated, my net force is equal to my centripetal force. It's got to point in towards the center of the circle. So I can, remember, this equation here just gives you the magnitude of the centripetal force. It's up to you to determine the direction. And for us, because we're at the top of the circle, centripetal force always points in towards the center of the circle, so I got to make this negative. All right, and so now it's just net force equals net force. I just found my net force, right? Remember, all of the net force is centripetal. So this is negative 13.3 m. That's got to equal my total force, which for me is my force of gravity plus the normal force. So add 9.8 m to both sides, and you discover that the normal force must be negative 3.5 times m. Okay. Now, what about at the bottom of the track? What about at the bottom of the track? So let's make a new drawing here. So when we're down here at the bottom of the track, what forces are there? Well, there's still gravity. It's negative 9.8 m. And there's a normal force, but now the surface of the track is below that. So that means that my normal force now has to be pointing up, right? Okay, now we're still moving at the same speed we were before, right? So we've still got the same mass, same velocity, same radius. We're going to have the same centripetal force. So that means, just like in the last example, my net force is still my centripetal force. It's 13.3 m. The big difference here is that now, because we're at the bottom of the path, remember your centripetal force acts towards the center of the circle. So for us, our centripetal force has to act towards the center of the circle, in other words, up. So this time my centripetal force is positive. So when I go back to my net force equals net force equation, let's see, we're going to get 13.3 newtons. That's our net force, right? Because of this. That's got to equal our gravity. Oops, sorry, I put newtons. It's not 13.3 newtons, it's 13.3 times the mass. All right, so that's got to equal our gravity plus the normal force. So now add 9.8 to both sides, and you get 23.1 m equals the normal force. Okay, notice how much larger the normal force is now, right? So the idea is, in this first example, when we're over here, both normal force and gravity are working together to produce the centripetal force, right? They're both pulling in towards the center of the circle. However, when you're at the bottom, gravity is actually working against the centripetal force, right? So we need to produce extra upwards force, some of it just to cancel out gravity, and then even more to produce a net force to produce the inwards acceleration. Okay? All right. So that is part one. Now part two wants to know what's the minimum velocity that they could have at the top of the loop without breaking contact with the track. This is a super common question. I bet this comes up every 2 years or so. They'll have a multiple choice question about this on the AP test, and it's a thing you should know to do. All right, so check it out. So when they're at the top of the loop, here they are at the top of the loop, right? Gravity's pulling them down with a force of negative mg, right, or 9.8 m. Okay. So the idea is once they leave the track, they're no longer in contact with the surface, so your normal force is 0, right? So the point at which they leave contact with the track occurs when the normal force is 0, right? So like, as long as there's even a little bit of normal force, that's telling us we're still in contact with the track. So once that normal force gets to 0, it means there is no contact with the track, all right? And so what this means is, at that point, your net force In other words, your centripetal force is now being provided completely by gravity. Okay? And so you get this equation. If all of my centripetal force comes from gravity, then I've got mv squared over r equals mg. The m's cancel, and I get v squared equals gr, or v equals the square root of gr. So for Homer and Krusty, we've got the square root of g, which is 9.8 meters a second squared, times the radius of the loop, which was, what, 1.2 meters, I think? All right, notice the units do work out here. We're going to get meters squared per second squared, and then when you take the square root, you do get meters per second. And if you solve it, you end up getting 3.43 meters per second. That's the smallest velocity they could have and still maintain contact with the track. All right, a similar question is if you imagine spinning, you know, like maybe you've got a yo-yo and you're spinning it around vertically. In order to make the rope not go slack, it's the exact same thing. The rope goes slack once there's no tension force, right? So to find this minimum speed you can have without having the rope go slack, the idea is at that point your gravity is responsible for all of your centripetal force. So it's the exact same solution, okay? All right, so we got one last example. Kabam. No, kabam. Kabam. All right, so these are the swings. This is an amusement park ride at Cedar Point. We've got these swings. I'm big in this so you can see it maybe a little bit better. There we go. All right, so what we're going to do is we're going to focus on a rider at the outside edge of the ride, okay? All right, so let's make kind of a neater drawing here. So here's that top support structure and the base, all right? And then our swing is coming out like this, all right? So what the problem tells us is that the chain, oh, so here's our rider, sorry. So the chain is 7 meters long. It tells us that the chain makes an angle of 50 degrees with the vertical, and it says the chain is supported at the top 5 meters from the axis of rotation. So this is 5 meters, okay? So as you spin around, the radius is actually going to be this distance. So it's going to be the 5 meters plus whatever this little horizontal component is from this triangle here. So let's draw that real fast. So we got doop, doop, doop. Here's our 50 degrees. This is 7. So if you use, okay, here's our right angle, sorry. So if you use sine, you can discover that this little distance here is 5.36 meters. Okay, and so what that means then is that our overall radius from here to here is 5 plus 5.36, so 10.36 meters. So that's our radius. Okay, and so the question wants to know what's the period of rotation. And we're really not given a lot to go on here, right? So let's focus on this for a minute. Okay, so here's our person at the end of the swing. What forces are acting on them? Well, let's see. There's the tension from the rope pulling them this way, and gravity pulling them down, right? And I think that's it. So what we're going to want to do then is make a note of our radius. I'm going to do a erase my drawing here. 10.36 meters is our radius. Oh, well, I guess I don't need to erase. I can do this. There we go. All right. So what I want to do is I want to take this drawing and replace it with a coordinate system that lies along our acceleration, right? And the idea is our acceleration is going to be in towards the center. So I want to stick with my standard x and y axes. So if I make a new drawing, what I get is this. Here's my person at the end of the rope. Gravity is pulling them down, and that tension force has 2 components. There's the tension in the x direction and the tension in the y direction, right? Now let's see, I know this is mg. Once you get up to top speed, you're not moving up or down at all, so that means this y component also has to be mg, right? I guess this is negative down here, right? Okay, so why does that help me? Well, why does that help me? That helps me because I know that my tension has horizontal and vertical components. So here's my tension. We just decided that the vertical component of our tension was mg, or I guess we could say 9.8 m if you prefer. And this guy here is 50 degrees, right? So I think I can use a little bit of trig to find my x component. So let's see, the tangent of 50 degrees is opposite over adjacent. So multiply both sides by 9.8 m, and you will discover that the x component is 11.7 m. So that's the x component of my tension. So great, but what is that tension doing? Well, remember that horizontal component of the tension is what's pulling our rider inwards and providing our centripetal force. Okay, so now centripetal force is Ftx. So mv squared over r is Ftx, which we had decided was 11.7 m. So the m's cancel. We know our radius. Remember our radius was what, 10.36? So multiply both sides. V squared is going to be 11.7 times 10.36. So multiply, take your square root, and your velocity turns out to be really close to 11 meters per second. And so the question wanted to know the period. So V is 2 pi r over the period. So 11, let me do the algebra first. So that means our period, is 2 pi r over our velocity. So 2 times pi times 10.36 over 11 meters per second. And it gives you pretty close to 5.9 seconds. All right. So the things that are new are we're going to have more forces at angles than we had in the past. And the big thing is these guys. This Krusty the Clown example is really the big deal, okay? Because you can certainly have more than one force responsible for your centripetal force. All right, so that's what's new. We'll talk more when I see you in class next. Have a good one.